on to the last part, which is the change of concentration with time. So we've been talking about rate laws, and rate laws compare how the rate changes when you have different concentrations. So this compares the rate and concentration. Now, a lot of the time, I want to know how long a reaction is going to take or how much is going to be left over a certain amount of time. And for that, we use what's called the integrated rate law. So we could use some calculus and actually determine these rate laws, but I'm just going to tell you what they are instead. So if I want to compare time and concentration, I use the integrated rate law, and you will see me abbreviate it as IRL. Okay, these are equations you will be given, but you have to be able to use them and know when to use which one. All right, so a zero order rate law, so this is a regular rate law, would be rate equals K, right? A first order rate law would be rate equals K times some reactant A. And then a second order rate law is rate equals K times some reactant A squared, or A times B, either way. So the units on K are always going to be the same, remember? So K's units here, since rate is K, would be molarity per second. Rates, or the K units for first order, is always going to be 1 over seconds, or you can write seconds to the minus 1. And the K units for second order are always going to be 1 over molarity seconds, or molarity to the minus 1 seconds to the minus 1. Okay, you might have kind of picked up on how that works the past couple of examples. Now, if I integrate these equations, I can come up with a new equation that can tell me what the concentration is going to be after a specific amount of time if I know the K value. So the integrated rate laws are as follows. For zero order is the concentration of A minus the concentration of A not meaning initial, equals negative KT. Okay, first order is a natural log relationship. It's the natural log of concentration of A minus the natural log of the concentration of A naught, meaning the concentration I started with, equals negative KT. And second order is 1 over, it's an inverse relationship, 1 over the concentration of A minus 1 over the concentration of A naught, my initial concentration, equals KT. So, well, how did we get these? If you actually graph the concentration of A over time, if it's a linear relationship, then you're going to get this graph, right? As concentration changes over time, the rate doesn't change. So a zero order graph, time versus concentration, is a straight line. Now, if the rate does change over time based on the concentration, then you're not going to get a straight line. You're actually going to get a line that looks like this, which is a natural log relationship. So if I graph the time versus the natural log, I get a nice pretty straight line. Okay, now if something is second order, you get that there's actually a drastic change in rate as the concentration changes. So as the concentration changes, or sorry, as time goes on, my concentration changes drastically. It's a 1 over or an inverse relationship. So if I graph time versus the inverse 1 over, I get a straight line in that regard. Okay, so essentially what these rate laws tell us is the relationship between the concentration and the rate, and we can use these to find a certain concentration at a certain time. So these equations you will be given, but you need to know when to use this one, when to use this one, and when to use this one. Okay, so these actually also apply to half-life. I'm going to give you half-life concentrations, specifically because a normal half-life for like a radioactive material is actually a first order reaction. And we can find the half-life based on the K. So I'm going to give you these. We're not really going to use these much, but if you, in case you need to find the half-life or how fast something decays over time, you can use these equations as well. So T1/2 means half-life, the amount of time for something to decay by half, is the concentration of A naught over 2K. Okay, the half-life in a normal radioactive relationship, which is a first order relationship, is 0.693 over K. And in a second order relationship, the half-life would be, oh, that was supposed to be a K. Sorry. K times T plus 1 over A naught. Most of the time, you're just going to see this one for half-lives. But I just wanted to give you the equations in case you needed them. Okay, So example number 7 says the decomposition of N2O5 is first order. I told you it was first order. So I know that all of this applies. Okay. It has a rate constant, or K, 4.8 times 10 to the negative fourth per second at 45 degrees Celsius. Remember, K changes with temperature. That's why I have to tell you what the temperature is. If the initial concentration is 1.65 times 10 to the negative second molar, what is the concentration after 825 seconds? Okay, remember, integrated rate laws incorporate time and concentration. So what I'm going to do is I'm going to use the integrated rate law for first order reaction, plug in my information. So I'm going to use the natural log of, I'm actually trying to find the new concentration at a time. So I'm looking for A, minus the natural log of A naught is my starting concentration, negative second molarity, equals negative K, I gave you K, is 4.80 times 10 to the negative fourth per seconds, times T, 825 seconds. Notice this is in seconds and this is in seconds. They do have to be the same, but I did drop my units. So if you do your algebra here, you are going to get that the time for this to occur, oh, sorry, not the time. We're looking for the concentration. Sorry. I'm going to do just one of the algebra steps. If you rearrange this, you get the natural log of A is negative 4.5. Remember, inverse of the natural log is e to the. So if you use the E equation, you should get the A is 0.011 molar, or 0.111 molar. Okay, now ask yourself, does this answer make sense? Well, I started with 1.65 times 10 to the negative second molar. So it makes sense that I have a little bit less than that. Awesome. Okay, part B, how long will it take for the concentration to reach 1 times 10 to the negative second? So how long means in this case, I'm looking for time, but I'm giving you the concentration I want to get to. So this time it's going to be natural log of 1 times 10 to the negative second minus the natural log of what I started with, which again is 1.65 times 10 to the negative second, equals negative K is a constant, so I'm just putting in the same number, times 10 to the negative fourth, times T. Okay, that one's pretty straightforward algebra. You should get the T is 1040 seconds. Okay, which makes sense because I'm trying to get to an even lower concentration, so it should take more time. All right, I want you to try example number 8 by yourself and then check your answer. All right, so since this one was second order, I used the second order integrated rate law, plugged everything in, got that the concentration for A is 0.0012 molar, and the time for B is 2,150 seconds. Okay, on to graphing. Now this is going to be really important because this is what you're going to do in lab to determine what order something is. Okay, so we talked about they have a relationship that's either a linear, natural log, or inverse. That's what we're looking for. Okay, so what you're going to do is essentially graphical analysis. You're going to graph it and figure out which graph is best. So if you're testing to figure out if something is 0, first, or second order, what you're going to do is you're going to change the concentration of the reactants and measure the product over time and graph it. Okay, so change concentrations, measure product over time, and then you're going to graph it and figure out if it's 0, first, or second order. Is it linear? Is it natural log? Or is it inverse relationship? Now, how are you going to measure the amount of product over time? We are actually going to use spectrophotometry because the product that you're going to make in lab has a specific color, or actually lack of color. You're starting with something that's colored. So you can tell that the concentration changes over time by measuring the absorbance. So one way to measure how much product you have over time is to use a spectrophotometer, again, which is what you're going to do in lab. There's other ways to do it, but if you have a colored compound, spectrophotometry is super helpful. You can figure out how much there's going to be, how much there is based on how much light shines through it. So what you're going to do is you're going to graph it, and then you're going to find your correlation coefficient, or that R squared value, right, on in Excel. So R squared tells you how linear your relationship is. Okay. We want an R squared value of 1. That means you have a perfect linear relationship. Now, of course, in the lab, that's not always going to work out. Anything 0.8 to 1 is good for R squared. All right, I would call that decently linear. You want 1, but yeah, anything in between there is pretty good. Okay. And then you're going to actually calculate the slope of the line, which can tell you the K value. So you're going to calculate slope of the line with Excel. So you don't have to do all the math by yourself. Remember, if it's linear, it's going to be y equals mx plus b. You can find your slope, all of that jazz. So you might get some graphs that look like this. You're probably not going to get anything that looks like this, but some graphs that look like this in the lab. And it's going to be really important that you're looking for the most linear. So these ones are very linear, right? You get an R is -1 and +1. And over here, I got a 0.9 and a 0.8. Those aren't bad. You can tell those are kind of linear relationships. This one, not so much linear relationships, and this one definitely not. So you should be able to identify if something's a linear relationship or not. Okay, so what you're going to do is you're going to get all your data, and then you're going to graph concentration versus time. You're going to graph the natural log of the concentration versus time, and you're going to graph the inverse of the concentration versus time. Okay, and then you're going to check whichever one is most linear, because if this one's most linear, then that means it's 0 order. If this one is most linear, that means it's first order. This one is most linear, that means it's second order. Okay, so you're going to pick whichever one is best, or which one gives you the best R² value. And then the slope is going to be your K value. In this case, if this one is slope is -K, this is -K, and this one the slope is K. You don't have to know negative or positive, just K is never negative, okay? So you're going to pick which one is most linear, and that's going to tell you if it's 0 first or second order. Okay, simple as that. So like I said, we're going to use Excel. I'm going to do this example here. I'm going to show you a couple of tricks for Excel, and then you guys can try example 10 by yourself, okay? So I gave you this data. I'm going to graph it in Excel. I'm going to have Excel calculate my natural log and my 1/, for me and graph it so I can find the slope and the R². So what I'm going to do is find that file so I can show you example number 9. And share this. Okay, so what I did here is I put the data that I have in here, okay? And then I created a graph. So if you look at this graph, I got an R² value of 0.8614. Yeah, not terrible, but that's concentration versus time. Now, what you can do in Excel is you can actually make it calculate for you. So I also want to graph natural log versus time and 1/, to see which one's the most linear. So what I'm going to do is I'm going to actually type in here, type equals ln, and then I'm going to click on this because it's going to do the function for me of the concentration. Awesome, calculated the natural log. Now all I have to do is click back on this. You see this little box down in the corner? You pull it down and it'll calculate all the natural logs for you. I'm going to do the same thing here with 1/. I'm going to put equals 1/, concentration. And then I will click back up here. I'm going to drag this one down again, and it calculated them all for me. So I'm going to graph this time versus natural log. Insert, scatter plot, this guy. Okay. I also need a trend line so that I can figure out which one's most linear. So you've probably done these before. If you need help finding it, let me know. Oh, look at that one. That's got an R² value of 1. That's probably right. So this was the natural log graph, so it's probably a first order. But I'm going to graph the other one just in case. Time versus 1/. Insert chart. I'm going to add a trend line for this guy with an equation in R². And would you look there? Okay, so I have all of my data. This one is obviously the most linear because the R² value is 1. And since this one is the natural log graph, that means it's first order because first order has a natural log relationship. So I'm going to go back to my notes. Find them. They're there. Okay, I'm not going to fill in the data because Excel did it for me, but what I got was that the R² value here was 0.8614. This R² value was 1, and this R² value was 0.8638. So that must have meant it was a first order reaction. The slope was negative 0.0002, so that means that that is my K value. So now if I wanted to write the rate law, I would write that rate equals K times, I said it was first order, so CH3 3, and C, first order. And I know that K is 0.0002, and the units for a first order reaction are always 1/seconds. So this is my answer. All right. So I want you to try to graph and figure out what the answer for example number 10 is, and then check back. Okay, so I graphed these and I got the most linear was the inverse relationship. So when I graphed 1/NO2, got that the R squared value was 1, the slope was 0.5431. So that means that my rate looks like this, and my K is 0.5431, and the units for K for a second order reaction are always 1/molarity per second. Okay, all right, so now you should try to do your group activity for practice. That'll be due in the next class period. And I'll also post the Chem 101 homework, which is really just a lot of practice that won't be due until we're completely done with chapter 13. Good luck.